In the long run, we can vary all of the inputs. Since we've assumed here that the two inputs for production are capital and labor, in the long run, we'd be able to vary both of them. So there'd be more than one way of producing the same amount of output Q. So you can make up, if you reduce the amount of capital you're using, you could use more labor to make up for it, or vice versa. So an example of production function that uses both labor and capital would be this Cobb Douglas production function. So if you use L units of labor and K units of capital, then the total output is L to the 0.5 times K to the 0.5. So if you fix some quantity Q bar that you want to produce, then you could draw a curve through all the different pairs of inputs, L and K, such that that pair of inputs gives you exactly Q bar units of output. This should again sound very familiar to you. So let's fix it at Q bar equals 6. So all of these things, all these pairs of inputs, so you use 1 unit of labor, 36 units of capital, or you switch the amounts of labor and capital. You use 36 units of labor and 1 unit of capital. Or maybe you use 6 units of each. Or 2 units of one, 18 units of the other. 3 and 12, 4 and 9. All of these various combinations of labor and capital will produce exactly 6 units of output. Again, this, like I said, this should seem very familiar to you. If you go back to when we talked about indifference curves, this is exactly the exercise that we went through. Instead of fixing the quantity of output, we fixed the utility level. The counterpart of an indifference curve is what we call an isoquant. The word iso refers to same, and we use quantity. For quantity, we use the term quant. So if we draw a curve through all the different bundles of inputs that give you the output of 6, we get this isoquant through all these bundles. So for higher values of output, we get higher isoquants. So what are some properties of isoquants? They're going to have some very familiar properties. They're just like indifference curves. So further you go in this direction, the higher the level of output. When we were talking about indifference curves, the further you went in that direction, the higher the utility level. They're not going to cross, just like indifference curves don't cross, isoquants don't cross. They're going to slope downwards, so you can substitute, that reflects that you substitute one input for the other. They can't be thick, but the biggest difference between indifference curves and isoquants, despite all these similarities, is that the numbers that we associate with the isoquants actually mean something. The numbers we associated with indifference curves were utility levels. And we've talked a lot about how the numbers that we use to represent utility don't actually mean anything. They're not measured in any meaningful units. But the quantity of output is measured in very meaningful units. They're measured in number of units of output. So it doesn't mean anything to say, I get utility of 2 versus utility of 4. Well, yeah, does it really mean that you get double the utility? No, it doesn't. It just means you get higher utility. But if I get output of 2 versus output of 4, it literally does mean I get twice the output. So the numbers here really do mean something. So let's look at some of the classical production functions and what the isoquants would look like. So Cobb Douglas is a very useful class of production functions. And just like we did with the Cobb Douglas utility functions, the Cobb Douglas production functions are going to be ones that we're going to see over and over again just because they make the math very easy. For a Cobb Douglas production function, we're going to have some parameter A, capital A, and parameters little a and little b, such that when you use L units of labor, K units of capital, the total output is going to be capital A times L to the little a times K to the little b. Now there's some differences between the Cobb Douglas production function and what we saw as the Cobb Douglas utility functions. We're not going to assume here that A plus B equals 1. Remember, the utility that we wrote down for Cobb Douglas was U of Q1, Q2 equals Q1 to the A, Q2 to the 1 minus A. In other words, we were assuming that B was just 1 minus A, so A and B sum to 1. And we're not going to make that assumption here. Now, the other important difference, very important difference, is that you can't observe a utility function, but you can observe a production function in principle. So you can collect output data and you can estimate these parameters. So if you want to think of the aggregate production of the US economy, for example, you would find that A would be 0.3 and B would be 0.7. Just like we've seen lots of different types of utility functions, there are lots of different production functions you could have. So a counterpart of perfect substitute's utility is a perfect substitute's production function. So let's suppose you're making French fries, then you could have two different inputs. You could have either Maine potatoes or Idaho potatoes. Now it doesn't really matter which one you use. You can produce, for every pound of potatoes that you use, you could produce a pound of fries. So the total output, if you use X pounds of Maine potatoes and Y pounds of Idaho potatoes, is going to be X plus Y. The total amount of potatoes you use is what matters. So we call this the perfect substitutes production function. This should be very familiar to you because it looks a lot like the perfect substitutes utility function. So what do the isoquants look like for these perfect substitutes production functions? Well, we're going to do the same thing as we did before. Let's fix the output Q bar and look at all the pairs of inputs X and Y that give you Q bar units of output. Well, if you use X and Y as your inputs, your output is X plus Y. So we want to find the X's in the pairs X, Y such that X plus Y equals Q bar. Well, if I solve for Y in terms of X, I get Y equals Q bar minus X. So varying Q bar and treating Q bar as a constant, we see that these are just straight lines of slope minus 1. And the intercept, the vertical intercept, is going to be Q bar. So what is the vertical intercept? The vertical intercept tells us if I use only input Y, how much of it do I need to use to produce Q bar units of output? Well, I need to use Q bar units of that input. So if I put Idaho potatoes on the vertical axis, Maine potatoes on the horizontal axis, for each quantity Q bar, I can draw an isoquant, which is just going to be a line of slope minus 1. Again, just like perfect substitutes, this production function, right now we're looking at this one. But in general, you can write down a perfect substitutes production function where you have some I times X plus J times Y. You could have production functions that look like this. And these would also be perfect substitutes production functions. And the way you would handle these is very similar to the way you would handle perfect substitutes utility. So the slope of, if you have f of x, y is ix plus jy, then the slope of the isoquant is going to be minus I over j. Now, we've seen perfect substitutes. What about perfect complements? Does it make sense to have perfect complements in production? Sure it does. Let's suppose what you produce are martinis. Well, if you want to produce a martini, you're going to need gin and vermouth. So every unit of output, every martini you produce, needs 5 parts gin and 1 part vermouth. So if you have G units of gin and V units of vermouth, how many martinis can you make? Well, you can make this many. Let's break that down a little bit. For every martini I make, I need 5 parts of gin. So if I have, let's suppose I had an unlimited amount of vermouth. I don't have to worry about the vermouth I have. So if I have G units of gin, I need 5 parts of gin for each martini I make. So if I have G units, I can make this many. And if I don't have to worry about the vermouth that I have, so I'm not limited by vermouth, then this is the number of martinis I would be able to make using G units of gin. On the other hand, each martini uses only 1 part vermouth. So if I have unlimited amounts of gin, but I only have V units of vermouth, I can make exactly V martinis. So which one is going to be the limiting factor? Well, I look at the smaller of the two. Which one of these, G over 5 and V, is smaller? That's the number of martinis I could produce, which is what I've written here. It's the minimum of V and G over 5. And that's the total number of martinis that one would be able to produce if you had V units of vermouth and G units of gin. So in general, you can have a production function of the form I times X, J times Y, and that's going to be a perfect complements production function. The key here is that you can't really substitute one input for another, and they have to be used in fixed proportions. Right? Here we have to use them in 5:1 ratio. So what do the isoquants look like? Again, they're going to be very familiar. If you remember the perfect complements indifference curves, they're going to look the same. So let's draw the isoquants for our martini maker. Look at this dotted line. This dotted line follows the equation G equals 5 times V. So that's when, along this dotted line, V and G over 5 are going to be equal to one another. Right? So if G equals 5V, if I divide both sides by 5, I get G over 5 equals V. So these two things are both equal when we're on this dotted line. Above the dotted line, I have more gin than I need because I'm limited by the amount of vermouth that I have. Below the line, I'm limited by the amount of gin that I have. So that's why I get these L-shaped isoquants. And they're going to have these corners along the dotted line where these two things are equal. Okay, now we've seen perfect substitutes, we've seen perfect complements. And of course, just like the indifference curves and just like utility functions, we could have all kinds of things between. The Cobb Douglas isoquants are going to lie between the perfect substitutes and perfect complements.